you're a regular viewer of VideoTec, by now you're probably aware of the extraordinary use of computers to control various systems on the Eagle Premier. In fact, if you were to combine the control modules and control units used on the Premier, you would have a computer with a power capability exceeding that of a typical personal computer. In this VideoTec, we're going to examine one more of the computer-controlled systems on the Eagle Premier, heating and air conditioning. This system is also used on the Dodge Monaco. The computer in this case is called the Air Control Module, or ACM, and it's found on Premiers and Monacos both with and without air conditioning. In this program, we'll first discuss system components and their operation. Then we'll look at diagnosis and testing of the system and AC system service. The session also includes information about a practice that you will need to become thoroughly familiar with if you expect to perform AC service in the future: refrigerant recovery and recycling. Let's start our look at system operation by discussing system controls and the ACM. Because the heating and air conditioning system controls and displays are used in self-diagnostics, it's essential that you understand their operation. Let's briefly review the operation on a vehicle equipped with air conditioning. The switches in the right-hand pod assembly, mounted on the steering column, allow a driver to operate the climate control system. A display module mounted to the right of the steering column in the instrument panel displays the selection. The temp switch allows the driver to select the desired in-car temperature. This temperature is displayed in the display window. The blower switch allows 4 blower speeds. The mode switch allows 3 AC selections and 4 heat and defrost selections. In addition, there's a button for activating the rear defroster and a front defroster button which operates independently of the mode selection switch. An English metric switch on the left side of the instrument panel allows the temperature to be displayed in Celsius and Fahrenheit degrees. The heater-only system uses controls and displays that are slightly different. Instead of a temp switch, a slide lever potentiometer sends a signal to the ACM. In addition, the heater-only display does not have a temperature readout, and of course, it lacks the AC modes found on the displays used on vehicles equipped with AC. All of the switches we've been looking at act as inputs to the air control module, which is located at the far right-hand side of the plenum assembly. Now, to understand how climate control works on the Premier and Monaco, we need to spend some time looking at ACM inputs and outputs as they occur on systems with AC. The control switch circuit, which is the first input we'll look at, uses a unique system to transform switch activation into input signals. 3 of the circuits between the air control module and the switch assembly supply the switches with 3 different voltages. These voltages can return to the ACM along 3 different paths, depending on where the switches are positioned. For instance, if the blower down switch is depressed, the voltage at input A to the switches returns at output B. If the rear defrost switch is depressed, the voltage returns at output C. And if the temperature up switch is depressed, the voltage returns at output A. The other voltages operate in a similar manner. Now, after receiving voltage signals from the switch assembly, the ACM signals the computer chip in the display module, which turns diodes on and off to change the display. When the air control module senses a ground at the English metric switch, the ACM changes the readout sent to the temperature display from Fahrenheit to Celsius, or vice versa. Also, as a result of the inputs from the switch assembly, the ACM routes vacuum to doors in the plenum assembly. 2 of the doors in the plenum control which of the plenum outlets are used. Another controls whether outside or inside air is drawn into the plenum. We'll see more of these doors later in the program. Another output of the ACM is the air mix door in the plenum. This door controls the amount of air passing through the heater core. It's operated by a 12-volt motor which receives current from the ACM. To sense air mix door position, the ACM uses a feedback system. The module sends a 5-volt signal to the air mix door position sensor. As door position changes, the sensor wiper moves across the sensor resistor, and the feedback signal changes. When the signal corresponds to the desired position, the ACM cuts off current to the motor. In positioning the air mix door, the ACM also makes use of inputs from the ambient and in-car temperature sensors. The ambient temperature sensor is located on the right radiator support bracket below the front bumper. The interior temperature sensor is located at the front of the instrument panel, just left of the glove box. These sensors are really thermistors that the ACM sends a 5-volt reference signal to. As temperature increases, resistance increases at the sensors, and the amount of voltage drop detected at the ACM internal resistors decreases, allowing the ACM to calculate temperature and adjust heating and cooling accordingly. Keep in mind that we've been covering the climate control system as it occurs on a vehicle equipped with AC. The heater-only system does not use the temperature sensors. Instead, the ACM on heater-only systems uses the position of the temperature select lever in controlling the position of the air mix door. There is a direct relationship between the position of the lever and temperature control. As a result, temperature control on the heater-only system operates in the same way as an electrically controlled manual system. Another input to the ACM is the clutch cycling pressure switch, located at the accumulator dryer. Clutch cycling pressure switch operation is closely related to AC clutch relay activation by the ACM. The clutch relay is located beneath a cover on the left fender well. The clutch cycling pressure switch senses refrigerant pressure on the low side of the AC system. The ACM sends battery voltage to the switch and monitors when the switch is completing a circuit to ground. The switch is closed when refrigerant pressure rises to about 42 psi. This tells the ACM to ground the circuit from the AC cutout relay, which results in compressor clutch operation. The cycling switch is open when low side pressure falls to about 25 psi. As a result, the ACM interrupts AC compressor operation and prevents the evaporator from icing up. Now, since refrigerant pressure falls with ambient temperature, the clutch cycling pressure switch also opens to prevent AC operation when the temperature is below approximately 48 degrees Fahrenheit. It's important to keep in mind that the clutch cycling pressure switch is the only pressure-sensitive switch controlling AC operation. There is no expansion valve or high-pressure cutout switch to start or interrupt compressor clutch operation. The input to the ACM is strictly from the low side and depends on refrigerant pressure, not evaporator temperature. It's also important to keep in mind that ACM operation of the AC clutch relay depends on more than just the status of the clutch cycling pressure switch. Obviously, one of these additional inputs is the mode selection signal from the switch assembly. But AC operation can also depend on input from and output to the fuel injection ECU. In fact, signals between the ACM and ECU occur on 3 different circuits. The engine temperature load circuit, which relays signals from the ECU to ACM, has 2 jobs to do. First, when the ACM is in an AC mode, the ECU lets the ACM know when a wide open throttle condition exists, so the ACM can open the ground to the AC relay, thus reducing the load on the engine. Second, when the ACM is in heat or heat defrost mode, the ECU lets the ACM know when engine coolant temperature is too low to provide heat from the heater core. The ACM then prevents blower operation. We'll talk more about blower delay later in this program. You may be wondering how the ECU knows which information it's supposed to be providing. Well, the answer is that the ACM tells it. Using the AC select circuit, when an AC mode has been selected, the ACM closes the select circuit, sending battery voltage to the ECU and signaling it to send load signals. Otherwise, the circuit is open, signaling the ECU to send a temperature signal. The third ACM-ECU link, the predict circuit, allows the ECU to anticipate AC compressor operation and to adjust the idle accordingly. Here's how it works. The ACM sends a battery voltage signal to the ECU 1/2 second before compressor operation begins. The ECU then adjusts engine idle RPM up. 1/2 second before compressor operation stops, the ACM opens the circuit. The ECU senses the change and reduces idle speed. In addition to its other outputs, the ACM also controls blower operation. The ACM does this by providing or interrupting grounds to 3 blower relays. The relays control 3 resistors, which complete the circuit from the blower and which can be inserted in series into the circuit. In other words, the relays provide a ground for the blower motor, which varies in resistance, depending on the number of resistors involved. In low, for example, the ACM provides a ground to relays 2 and 3, but not to relay 1. As a result, current from the blower motor must flow through all 3 resistors to reach ground. This reduces blower speed. In high, the ACM provides a ground only to relay 1. This bypasses all 3 resistors and results in a direct path to ground for the blower motor. The blower relays are located at the bottom of the plenum, to the left of the ACM. The resistor block is located inside of the air recirculation door. Earlier, when discussing the ACM-ECU links, we mentioned something called blower delay. At this point, we need to explore this unusual feature of the Premier&Monaco climate control system in greater detail. First, with a climate control system equipped with AC, the following conditions must be in effect for the delay to occur. The controls must have been left in heat or heat defrost. The coolant temperature must be low. The ambient temperature must be below 70 degrees Fahrenheit. Both the ambient temperature sensor and ECU ACM lines must not be opened or shorted to ground. The ACM will delay blower operation until coolant temperature reaches 120 degrees Fahrenheit. Now, a driver can override the blower delay by changing either the set temperature or mode, or by depressing the blower up switch. The final input and output of the ACM controls the operation of the rear defroster. The input to the ACM is the rear defrost switch in the pod assembly. We discussed the operation of the pod assembly switches earlier. When the ACM receives a signal that the rear defrost switch has been pushed, it completes the ground for the rear defrost relay, sending current to the rear defrost grid. A timer on the air control module limits the ground to 10 minutes on the first activation and 5 minutes on the second. The rear defrost relay is located on the bottom right side of the instrument panel. Well, that about covers heating and air conditioning controls and ACM operation. In the next segment of this program, we'll discuss Plenum Operation in greater detail and take a look at the components of the AC system. Earlier, when discussing ACM outputs, we briefly covered plenum air door operation. Now, starting with the vacuum-operated doors, let's take a closer look at exactly how the plenum directs air where it's needed. The air recirculation door, located just to the left of the air control module, has 2 positions. One allows outside air to enter the plenum, the other recirculates air from inside the car. The spring-loaded vacuum actuator operating the recirculation door has only one vacuum line going to it. The mode door has 3 positions. One directs all air from the air mix door to the heater and defroster outlets. A second splits the air between the heat defrost outlets and panel outlets. A third position routes all air to the panel outlets. The vacuum actuator operating the mode door has 2 vacuum lines connected to it. Both lines must have vacuum to move the door to the panel outlet position. The heater defroster air door also has 3 positions. In its fully retracted position, the door routes air only to the heater outlets. At mid-travel, air flows to both the heater and defroster outlets. When fully extended, the door routes air only to the defroster outlets. Like the mode air door, the heater defroster vacuum actuator has 2 vacuum lines connected to it. Both lines must have vacuum to move the door to the fully retracted position. The VideoTec reference book contains vacuum charts for both the heater-only and AC climate control systems. The charts detail where you can expect to find vacuum at the actuators as the system is set to different modes. Unlike the other doors, the air mix door located upstream of the heater core is not vacuum operated. Instead, as we saw earlier, a 12-volt motor moves the air mix door. The ACM controls the motor by means of a feedback system. This allows the ACM to position the door precisely to achieve the desired air temperature at the outlets. Now, let's take a look at the location of the Premier Climate Control System's AC components. As we do so, we'll review the basic functions of each. The first one, the evaporator, is located in the plenum upstream of the heater core. When the AC is operating, air passing through the evaporator turns the liquid refrigerant inside into a low-pressure gas. The refrigerant extracts energy from the air as this occurs, so the air drops in temperature. The accumulator dryer is located in the right side of the engine compartment. It has two jobs to do. One is to separate liquid refrigerant from refrigerant gas so that no liquid finds its way into the compressor. The other job is to remove any moisture from the refrigerant. Located on top of the accumulator dryer is the clutch cycling pressure switch. Beneath the switch is the low-pressure gauge test port. The operation of this switch was described during the discussion of ACM inputs and outputs. As mentioned earlier, the switch is normally open at about 25 psi and closes at around 42 psi. From the accumulator dryer, refrigerant proceeds to the compressor, which moves refrigerant through the system and changes it from a low-pressure gas to a high-pressure gas. The compressor on Premiers and Monacos uses a wobble plate to drive 7 pistons. On the compressor head is a high-pressure relief valve. The relief valve vents refrigerant to atmosphere when excessive pressure develops on the high side of the system. From the compressor, high-pressure refrigerant moves to the condenser, where air extracts heat from it. This causes the refrigerant to condense into a liquid. From the condenser, refrigerant flows to the orifice tube. Now, the orifice tube is located in the line between the condenser and evaporator. The orifice separates the high and low pressure sides of the system and meters the amount of liquid refrigerant flowing into the evaporator. If you have occasion to replace AC components on a Premier, you'll find that the spring lock couplings are a little different from connectors you've seen on other systems. The coupling uses a garter spring and cage to lock the flared end of the female fitting over a male fitting. Disconnecting the couplings requires the use of a special tool. To disconnect the coupling with refrigerant removed from the lines, fit the tool over the coupling with the spring release part of the tool over the female side of the coupling. Then push the tool into the cage opening to release the female fitting. Before reassembling the spring lock couplings, make sure the garter spring is in the cage of the male fitting. And if you decide to use the indicator ring, insert the tabs of the ring into the fitting. Since the O-rings are made of a special material, use only O-rings specified for the spring lock couplings. Lubricate the new O-ring seals and the male and female sides of the connector with refrigerant oil. Then push the two halves of the coupling together using a slight twisting motion. When the two sides engage, you'll hear a click, and if used, the indicator ring will pop off to indicate the connection is secure. The Premier&Monaco AC system is designed to hold about 36 ounces of R12 refrigerant. It's important that the right amount of refrigerant is in the system, and the refrigerant is kept free of moisture. If there is too little refrigerant, the system will not cool the interior of the car properly. If there is too much, damage to the AC system components can result. In the presence of water, R12 can form acids, which will corrode system components. It's equally important to have the correct amount of oil in the system. The Premier&Monaco AC system is designed to use 240 cc's of refrigerant oil, plus or minus 15 cc's. Too much or too little oil in the system can cause damage to the compressor. Next, we need to look at climate control system diagnostics. We'll begin with troubleshooting system controls and the plenum. With the complexity of the Premier&Monaco climate control system, you might think that troubleshooting is extremely difficult. Fortunately, the built-in self-diagnostics can tell you a lot about what is occurring in the system. The self-diagnostics are most effective when used as part of a comprehensive troubleshooting procedure, such as that contained in the heating and air conditioning section of the Premier&Monaco service manual. The primary reason to enter self-diagnostics is to determine the cause of a fault indication on the display module. On heater-only systems, the display flashes a mode indicator for 5 seconds to indicate a fault. On both systems, if the cause of a fault is eliminated, the ACM will discontinue the fault indication after 60 cycles of the ignition key. Disconnecting the battery will also discontinue the indication. There are 4 modes in self-diagnostics, and these modes correspond to the 4 blower motor speeds and are indicated by the LED displays for these speeds. The VideoTec reference book contains a chart of the diagnostic modes and what each checks. It's useful to keep in mind that modes M2 and high are generally used as a follow-up when a fault is discovered using the low and M1 modes. To enter self-diagnostics, first turn the ignition key to the run position. The engine can be running or stopped for self-diagnostics. Then select the climate control mode which prompted the complaint. If you're unsure of which mode is involved at this point, select an AC setting so that the clutch circuit can be checked. Next, simultaneously press and hold the blower speed switch up arrow, select switch left arrow, and front defrost switch. After about 3 seconds, when all of the diodes in the display light, release the switches. The low blower speed indicator will flash at this point, indicating that the system is in the low mode of self-diagnostics. By the way, you can exit the self-diagnostics the same way you entered, by pressing and holding the blower speed up arrow, the select switch left arrow, and front defrost switch. You can also exit by turning the ignition key to the off position. In the low self-diagnostic mode, the climate control display mode lights can indicate no faults in the circuits checked, or they can indicate faults that are a result of an ambient temperature sensor circuit open or grounded, an air mix door that is not operating properly, or an air mix door feedback circuit that is open or grounded. For example, if the off segment is lit, it indicates that no faults have been detected in the circuits which have been checked. If the heat defrost segment is lit, the fault is an air mix door feedback circuit that is open. To move from the low to the M1 diagnostic mode, press the blower up arrow and release it. The low and M1 lights will flash to indicate you have entered the M1 mode. Now, part of the M1 mode checks for faults in the in-car temperature circuit and the temperature lever circuit on heater-only systems, once again using the mode indicator lights to signal faults. As in the low mode, the lit off mode indicator signifies the absence of a fault in the circuits tested. But if, for example, the max mode indicator is lit, it indicates an open in the in-car temperature sensor circuit. The other part of the M1 mode checks the status of the AC clutch, the clutch cycling pressure switch, and wide open throttle signal from the ECU. The readout for this part of the M1 mode appears in the temperature display. For example, OP indicates that the clutch cycling pressure switch circuit is open. Later, we'll look at using this part of the M1 mode to troubleshoot a compressor clutch that doesn't engage. To enter the M2 diagnostic mode, once again, press the blower up switch and release it. The 4 sub-modes in M2 move the air mix door through its entire range and, on AC systems, indicate the voltage the ACM is receiving on the feedback circuit. The ACM then uses these voltages to calculate air mix door travel. This is an important feature of self-diagnostics, since the air mix door motor should not be removed from the plenum for diagnostic purposes. The motor is calibrated to the ACM, and removing it and operating it will cause the system to go out of sync. Because of this, the motor should not be operated unless it is in the plenum. If the feedback circuit from the air mix door is open or shorted to ground, the ACM cannot enter the M2 mode. This condition should have been indicated by lit segments in the low diagnostic mode. As a result of an open or shorted feedback wire, the air mix door will not move, the 4 sub-modes cannot be entered, the mode indicators will not light, and the set temperature digits will display a question mark. If sub-mode 1 is entered, however, the bi-level indicator will light, and the ACM will position the air door to correspond to the present temperature setting of the system. At the same time, the temperature display will indicate the feedback voltage from the air door without a decimal point. This voltage reading and the readings to follow will be used by the ACM to calculate the travel in degrees. It is this final reading that indicates whether the air mix door is working properly. Now, to enter sub-mode 2 of M2, press and release the mode select switch right arrow. At this point, the display will change to vent, and the ACM will move the air mix door to the stop at the full hot position, or to a position 45 degrees from the center of travel, whichever occurs first. The temperature display will again indicate the feedback voltage. To advance to sub-mode 3, once again press the select switch right arrow and release it. When the system enters sub-mode 3, the display will change from vent to heat, and the ACM will move the air mix door to the full cold position. Once the door stops, the temperature display will indicate the feedback voltage. As mentioned earlier, this is one of the readings used by the ACM to calculate a final readout. To advance to sub-mode 4, once again, press the select switch right arrow and release it. In sub-mode 4, the ACM will move the air mix door to the same position as in sub-mode 1, the position representative of the present temperature setting. The ACM will then calculate the range of travel in degrees and indicate it in the temperature display. If door travel is between 45 and 75 degrees, the air mix door and motor are okay. If the readout is less than 45 degrees, either the air mix door is stuck or the motor is not working properly. Now, to enter the final diagnostic mode, high, press the blower speed up arrow once again and release it. Now, in high, the ACM displays the inputs from the ambient and in-car temperature sensors. And by comparing these readouts to actual temperatures, you can check the accuracy of the sensors. Once the first of 2 sub-modes of high is entered, the final blower motor indicator will light and flash with the rest. In sub-mode 1, the norm indicator is lit, and the temperature display will show the outside temperature as indicated by the ambient temperature sensor. Now, if there's a question mark in the display, the ambient temperature sensor circuit is open or grounded. To check the accuracy of the in-car temperature sensor, press the select switch right arrow. The mode indicator display will change from norm to bi-level to indicate the change, and the in-car temperature will be displayed. Now, as in sub-mode 1, if the circuit is open or grounded, a question mark will appear instead of a temperature reading. Once a repair is made, it's easy to erase faults from the system. Simply enter the mode at which the fault was discovered, low or M1, and press the front defrost switch for 5 seconds. The mode light which indicated the error will flash while the switch is depressed to indicate the fault clearing attempt. If the cause of the fault has been corrected, the mode light should go out when the front defroster switch is released. Self-diagnostics is a great feature of the Premier climate control system, but in some cases you may have to resort to more conventional means to find the cause of a problem. For example, suppose that there is no heating or air conditioning at all. Your first check should be at fuse 2 in the fuse panel. If the fuse is intact, your next check should be at the ACM connector terminal D13. This is the battery voltage feed to the ACM. Now, with the ignition switch in run, also check for voltage at terminal D3 on the ACM connector. This is the ignition switch feed to the ACM. If there is no voltage at D3, check fuse 10 in the fuse panel and the circuit between fuse 10 and terminal D3. Next, check the ground for the ACM at D7. You can do this by using the terminal as a ground for the voltmeter while probing a known good battery feed wire with a voltmeter positive lead. Finally, check the 5-volt reference signal wire from the ACM to the switch assembly. This is connected to terminal E3 of the switch assembly. For some checks, you can use the readouts from the self-diagnostics to help you narrow down the possibilities. For example, suppose the AC clutch is not engaging. If the AC clutch status readout indicates the clutch cycling pressure switch is open when it should be closed, the problem is in the switch circuit, or low refrigerant. You can narrow down the possibilities by checking for voltage at the switch when the ignition switch is in run. If there is voltage, the switch ground, or low refrigerant is to blame. We'll see a procedure for checking for low refrigerant later in this program. If the status display indicates that the clutch is on when it really is off, you know that the ACM is providing a ground for the AC clutch relay coil, and you'll need to concentrate your attention on the contact side of the clutch relay and on the compressor clutch itself. This means, for instance, connecting a voltmeter across relay terminals to check the battery feed to the contacts on one side of the relay and the compressor clutch ground on the other side. The troubleshooting charts in the service manual can provide you with procedures to use in diagnosing the conditions we have looked at, as well as other conditions. Next, we need to look at items to keep in mind during AC service. When diagnosing no cooling or insufficient cooling, start with the basics, such as checking to make sure the compressor clutch engages. Earlier, when we looked at some of the things that can prevent a compressor from operating, we concentrated on electrical causes. But as mentioned, one of these causes, an open in the clutch cycling pressure switch circuit, can also be caused by low system charge. One way of determining if system charge is sufficient to close the switch contacts is by connecting a low side gauge to the Schrader valve under the low pressure cycling switch. Make sure the gauge connector has a service valve depressor pin. With the engine off at higher ambient temperatures, if the system is fully charged, the gauge should register sufficient pressure to close the contacts in the switch, approximately the same PSI as the ambient temperature in Fahrenheit degrees. Now, if the compressor engages, but there is a complaint of insufficient cooling, be sure to check panel discharge temperatures. For an accurate check, make sure the in-car temperature is high enough to trigger maximum cooling. Also, keep in mind that as ambient temperature and humidity rise, discharge temperature will rise. So your customer shouldn't expect Arctic air from a discharge on the hottest, muggiest day of the year. When dealing with insufficient cooling, don't overlook causes outside of the AC system, such as an engine cooling fan that isn't operating or a loose drive belt. Now, oil near fittings or connections indicates the system has been leaking. One sign that low refrigerant is the cause of insufficient cooling is a compressor clutch that cycles rapidly. Feeling the evaporator inlet and outlet during AC operation will help confirm low charge in the system. On a system that has close to a full charge, the outlet will be 28 to 40 degrees Fahrenheit and will feel slightly colder than the inlet. On a partially discharged system, the inlet will either be warm or it will be colder than the outlet tube. Now, there are several ways to leak test a system. One involves bringing the system back up to charge and using an electronic leak detector. One way to check a repair involves discharging and evacuating the system, and then checking the gauge to see whether the system will hold a vacuum. Now, besides low refrigerant, the clutch cycling rate and clutch on and off times can help you diagnose other conditions. Refer to the clutch cycle time evaluation chart in the heating and air conditioning section of the service manual. And for a detailed procedure for troubleshooting insufficient cooling, see the flow chart in the same section. Now, before we conclude our AC tips, there are two more items we need to discuss briefly. The first is concern with orifice tube replacement due to system contamination. Now, in the past, when servicing an AC system that had been contaminated by, say, compressor debris, you would have had to flush the system with large amounts of refrigerant to make sure that a new orifice tube would not be plugged. With an increased emphasis on sound environmental practices during AC service, the flushing procedure is no longer an acceptable way to deal with contaminants. As a result, Chrysler has now made available an orifice tube which is part of an inline filter and which eliminates the need for system flushing. To install the orifice tube and filter, you'll need to first remove the old orifice tube. So after discharging the system, disconnect the liquid line spring lock coupling at the condenser outlet. Then remove the orifice tube from the end of the line using tool 6146 and reinstall the line on the condenser. Next, cut a 5-inch section of hose out of the liquid line between the condenser and the evaporator. The cut must be made in a straight section of line close to the evaporator. Be sure to cut the hose ends square and make sure no burrs or shavings remain that could contaminate the system. Next, slide the clamps from the orifice tube filter kit on the hose ends until the spacer bar ends rest against the hose ends. Then, force the ends of the orifice tube filter into each hose until the filter shoulders touch the hose ends. Make sure the orifice tube side of the assembly is closest to the evaporator. After making sure the spacer ends still rest against the hose ends, tighten the hose clamps to 45-inch pounds. The second AC service item concerns keeping the correct amount of refrigerant oil in a system during compressor replacement. Keep in mind that a certain amount of oil will stay in other system components, so installing a replacement compressor that is filled with oil may overload the system. As a result, before installing a new compressor, be sure to measure the amount of oil that was left in the old compressor. If you find that the oil is contaminated, be sure to install the new orifice tube filter described earlier. Then, drain the oil contained in the new compressor and put back into it the same amount of oil that was left in the old compressor. This helps to ensure the amount of refrigerant oil in the system remains the same. Well, that about wraps up this part of the VideoTec program, Premier Heating and Air Conditioning. Stay tuned for some important information about a practice that will change the way you do AC service, refrigerant recovery and recycling. And be sure to join us next month when we'll cover the Talon all-wheel drive system.